Okay, so good afternoon, everybody. I'm going to start right now because I'm not sure I'm going to be able to finish today. We have a long way to go today, okay? So I'm going to talk today about thermosolar power plants. Actually, what we're going to do today is try to simulate the conceptual design, to develop the conceptual design of a thermosolar power plant. Okay, so we're trying to configure our power plant in terms of some preconditions, such as the necessary power. Okay, the surplus energy that we're going to sell and make money out of it. Okay, so just to remember, this is one of the class related to thermal conversion, thermal energy conversion. As I showed you before, it's always like this. You have a thermal source and a cold source or a cold absorber, which is always the environment. Okay, and as our heat supply, our thermal source, we already analyzed the possibility of having some chemical reaction, such as a combustion reaction of coal, oil, or gas. We also saw nuclear reactions, and today we're going to consider this possibility here. We have sun energy, which is captured and concentrated, and this solar energy will provide the necessary heat to a thermal machine, which will convert to Exergy. Okay, so let's first try to take a look at this conceptual design of our power plant. It's like a tutorial class, okay? And well, let's see. But first, you will see further on that we're going to need to know the exact position of the sun in a given day of the year, in a given time of the day, hour of the day. So this leads us to take a look at celestial mechanics. So part of the class is going to be on celestial mechanics, which, by the way, applies also to photovoltaic power plants. So that's the interesting part of this class, and that's why I have so much to say, because we're looking at thermal power plants that uses sun energy as a heat source, but part of the subject that we're going to elaborate today also works for photovoltaic power plants, okay, and related to celestial mechanics. And this is, just to repeat, to know the exact position of the sun in a given hour of the day, in a given day of the year, okay? That's our objective. So coming back to our power plant, the main subsystems of a thermosolar power plant we can divide in three. We can focus on three. First, what we call collectors, concentrators of solar energy, and it is related to the primary cycle, to the primary part of the solar plant. These collectors / concentrators can be fixed panels. We're going to see these in details. Or they can be as heliostats. This means that you have some mechanism, a motor for instance, that will change the configuration of these panels in order to follow the position of the sun. Okay? You also need to have some kind of thermal storage to assure dispatchability, because you know at night you don't have sun and you still have to produce and dispatch energy to the grid. So you have to store energy not only at night but also when you have a cloudy day, for instance. So a second main subsystem is an energy storage system. And well, the third subsystem is a traditional, classical thermodynamic conversion cycle, the secondary part of the power plant. If we take a look at a Sankey diagram of the incident solar energy linking to the surplus energy, you see that you have losses, by the way, okay? And those losses are related to the collectors slash concentrators. So it is related to thermal efficiency or mechanical efficiency. Okay. Then you have losses related to the second law of thermodynamics. This is thermodynamics efficiency. Okay, so this is in a very broad view of power plant, and we're going to take a look in details, all these parts of the power plant. Okay, so in terms of its architecture, we have a primary cycle with possibly with heliostats, which somehow they follow the sun on the sky. So that's why we need celestial mechanics for this subject, because we need to know where the sun is going to be at a given time, at a given day. Okay, and well, this is to operate the power plant, but before that, in order to design the power plant, you need to know how much sun you're going to get in average in a year, for instance. And to do this, we have to integrate the solar energy during the hours of the day, during the days of the year. Okay, so again, that's why we need celestial mechanics. So the primary cycle, or the primary subsystem, actually is composed of a working fluid, here in red, okay, which is heated by the collectors and then releases this heat to the secondary cycle. Okay, so it cools down and then it's pumped back to the collectors. Okay, you also have a storage system here. We're going to detail this further on. Okay, so part of the heated working liquid, you can store this in a reservoir, for instance, and part you can use to supply heat to the secondary. If you don't have sun for some reason, because it's night or because it's cloudy, okay, you can use this heated liquid here in order to supply heat to the secondary. Okay, so the primary, okay, the storage system, and the secondary, which corresponds to a traditional thermodynamic conversion cycle. Okay, so we already seen this, so there's no problem here. Okay, in terms of statistics, let's say like this, these kind of plants range from 1 to 300 megawatts and have a capacity factor between 20-25% in average, but this varies a lot. For instance, here in Brazil, in Chapada do Araripe, as I already mentioned, you're near the equator, so this is good, we're going to see. But you also have very few clouds in this region, so the capacity factor is high. Okay, 20-25% is an average number, just to give you an idea of how low this can be. Okay, the capacity factor. Okay, so we're trying to focus on these three subsystems. First, let's start on the collector / concentrator possible geometries. Okay, so first we have what we call solar towers plus heliostats. Let me zoom here to show you. A solar power plant like this, actually you have a tower here with a collector, and you have a series of, actually they are flat mirrors, okay, flat mirrors. And they move individually, each of these mirrors, they move in order to reflect the sun, the solar energy, to a point here on the tower. Okay, so this one main characteristic of this configuration is that you achieve very high temperatures at this point here. Okay, you can melt steel, for instance. This is good because you know, if you have high temperatures here, your thermodynamic cycle is going to be more efficient, because the higher temperature, the temperature of the hot source is increased, and we know that the thermodynamic efficiency increases like this. So this is one possible configuration. Okay. Another possible configuration is linear collectors, such as Fresnel Fresnel lenses, actually, and they are composed of a series of again flat mirrors. Okay, flat mirrors, but they move individually. Okay, in order to concentrate the sun's energy in this line. Okay, so in the solar tower, all energy is concentrated on a point. Okay, and in here, in this situation, the solar energy is concentrated on a line. Okay, in this line you have a tube. Inside of this tube you have the working fluid of the primary. Okay, we're going to see this. And the Fresnel system, actually, those are flat mirrors, and they are able to move individually in order to focus the energy on this line. Okay, you also may have what we call parabolic froth. Okay, froth in Portuguese. In Portuguese, we use the word calha, okay, or coxo as for the cattle, okay. So let me focus here in order for you to see. The difference is that you don't have a series of flat mirrors. You have only one parabolic mirror here, okay, and the focal point of this parabolic mirror, is also a line. Okay, the collector tube is running along this line here, and you have a motor or a mechanic system that is able to turn this mirror in order to follow the movement of the sun. Okay, you also have a fourth kind of system, which is different. I'm listing here just for information, because it's not applicable for our situation here. Okay, is a parabolic disc plus a Stirling engine. So you have a disc. It's also a heliostat because it follows the position of the sun. Okay, but instead of absorbing the solar energy at the focal point by means of a working fluid, you have a Stirling engine placed here. So it converts directly the solar energy to electricity. Okay, so it's a direct electricity conversion. And a Stirling engine, I think you remember, I already showed you, I brought a Stirling model here for you. It's actually it's a reversible cycle, as it is the Carnot cycle. And so it's very efficient for energy conversion, especially at low temperature differences. Okay, so it's very convenient, but it's not applicable for the case that we are dealing today. Okay, just for your information. So the four types of solar concentrator geometries. Okay, and just an explanation. The collector here. Let me focus again. The collector here actually. Let me get here. Okay. The collector is this device here, in this case a tube, okay, which will collect the solar energy. The concentrator is composed by the mirrors, and the main objective is to concentrate sunlight. Okay, so it's like a lens, and so it's going to increase the energy flux that is arriving at the collector by a factor of 10 or 50. It depends on the collector. Okay, we're going to see this in more details in a moment. Okay, taking a closer look at the collector. Okay, there were several types a few years ago, but today this kind of became a commodity. So it's a vacuum tube. We're going to make a thermal analysis of this system. So you have a tube. Okay, the internal tube here, and the fluid. The primary fluid flows inside the tube here. So the objective is to heat the primary fluid, which can be oil or pressurized water or even salt, okay, liquid salt. And well, the outer surface of this tube is black in order to absorb the maximum, have a maximum absorbance, okay. and outside you have a glass tube, and the space between the inner tube and the glass tube has vacuum, okay, in order to avoid heat losses due to convection, okay. So this is produced in very large quantities, so it became very cheap actually today. I remember something like 15 years ago, this was very expensive, but today, due to scale economies, it became very cheap. So it's a very interesting solution for the collectors. Okay, you can buy these kind of tubes even for your homes. You can build solar collector for water heating at home with this kind of tube, no problem. Okay. Yeah, so let's take a look. Let's analyze how this works. Okay, so this sketch here, you have the working fluid here. Okay, oil or salt. You have the collector tube properly here in kind of a yellow. I don't know what color this is. Okay, you have vacuum here, and you have glass tube here. Okay. The total energy that arrives at the collector tube in terms of watts per square meter is going to be multiplied by the concentration factor, okay? Because of the amount of area of mirrors that is reflecting energy to this point here, okay? In terms of losses, or in terms of the total energy that is arriving at the collector, let's say that G0 is the sunlight, the sun energy, the sun flux, okay? And this refers to a given hour of the day, to a given day of the year, okay? So this varies with the time and also with the date, okay? So we multiply this by the concentration factor, which, as I said, maybe 10, 20, 15, depends on the geometry. It's only a geometrical factor. And it's going to arrive at the outer surface of the glass tube. And as I hope you can see, you have several kinds of losses. You have absorption losses. This means that this energy is going to be absorbed by the glass. It's not perfectly transparent, so it's absorbed by the glass. It heats, its temperature rises a little bit compared with the environment temperature out here, so it's going to lose energy through convection. Okay, you also have reflection. The tube, as I said, it's not perfectly transparent, so it may reflect some of this energy that is arriving here. Okay. But when it enters the vacuum here, okay, so it goes right through the absorber tube, you also can have radiation losses, and also convection losses, because I said there's vacuum here, but this vacuum is not perfectly, and with time the system ages, and you start having some leak of air to this region here, so you may have convection. Okay, you may have convection losses and all kind of losses actually. Okay, so in terms of balance here of the losses, 6.5% is due to reflection, 1.8 is due to absorbance, reflectance, emittance, and thermal losses. By thermal losses, I mean, I'm going back to, I mean losses through these connection parts, connections between several tubes. Okay, you may have heat coming through the material here by conduction, and then you may have losses through convection here. Okay, so this accounts for roughly 1%, and total losses is roughly 20%. Okay, so by accounting all of this, the net solar energy flux that effectively arrives at the absorption transportation fluid is, we're going to name this G. Okay, so it's the concentration factor times the mean solar incidence times this efficiency, okay, or 80% in this case, the thermal efficiency, okay. Just a remark here, I'm trying to prepare some working formulas for our conceptual design. That's why I'm giving you all these details, okay. So now we know how much energy is available for the fluid, okay. The fluid is this kind of purple circle here, okay. So it's G0, okay. And the amount that is going to be absorbed and then afterwards delivered to the secondary, we need only to multiply by the area of absorption. An important remark here is that the area actually corresponds to what we say the projected area. Okay, let me get my pen here. The projected area is this area here, okay. This dimension here is D. Oh, sorry, I'm using not the pen. So this dimension here is D, and the total length of the absorber is L, okay. So this term here is actually the total absorption area, okay. And since the tube is circular, the sun may be coming from other directions, you always have D times L as the absorption area. Okay, we're going to use this formula in a while. Okay, let's move to take a look at the architecture of our system. Okay, so as I mentioned, we have this collector tube. So L is the total length here. The diameter is D. Okay. And our working fluid, the working fluid of the primary cycle has a flow rate M primary here, okay. It enters at TE, and at the output it's heated to TS, okay. So, and then it releases heat to the secondary, so it cools down to TE, okay. So the primary cycle, the fluid is cycling here, okay. It does only this. Of course, the actual system is a little bit more complex than this, but for our analysis here, this is okay, okay. So the primary is simply like this, from TE to TS, then to TE again, okay. You're going to be cycling like this. And the secondary is actually, as I mentioned, a thermodynamic cycle. Okay, we're going to use a very simple cycle, a Rankine cycle with steam. Okay, and I already have some labels here in order to calculate the corresponding thermodynamic states when we're going to define this cycle. Okay, so what we're going to do is try to make this analysis by different parts. First, let's analyze the primary here and the collector. Okay, so if we apply the first law of thermodynamics here, the amount of heat absorbed, this quantity Q here actually is this quantity here. Okay, now I'm just looking at the fluid. Okay, so what happens to the fluid when it absorbs this energy Q? Okay, its temperature varies from TE to TS, and the first law of thermodynamics tells us this. Okay, so it's the flow rate times the specific heat at constant pressure times delta T. Okay, this is first law of thermodynamics. From this formula, you can calculate TS, okay, just isolating TS, and by replacing Q from the previous slide, okay, from the solar collector, we have this formula, working formula here. Okay, so TS is equal to TE plus something. Okay, this is the amount of heat that is being transformed into a certain delta T. Okay, this is delta T. it's worth writing this down. So this term here is delta T. Okay, and I just saw I wrote E and it's G0. Okay. Okay, right now we don't know, we don't have a definition for TE, we don't have a definition for TS, but we're going to use this formula in a few moments, okay? Okay, so it's as simple as this, and but we have to take something into consideration here, okay? About TS. As I mentioned, the efficiency of the thermodynamic cycle is maximized by increasing TS, okay, which implies in augmenting the concentration factor and other things that we're not mentioning. Okay, first, why increasing TS increases the efficiency of the thermodynamic cycle? Because the lower temperature here is fixed, is the environmental temperature, and the maximum efficiency so depends only on the higher temperature, T3, okay, which is close to TS. So if we have a very high TS, we're going to have a very high T3, okay, at the limit they can be the same, and by increasing T3, we're going to increase the overall first law efficiency, okay? To do this, I have to concentrate solar energy, okay? You can see this conclusion here, you can see from this formula. For instance, if you increase the concentration factor, this term here, it's obvious that TS increases also, okay? So, in terms of the possible collectors that we have as a working choice, the linear collectors may increase by 50, the tower by 1,000, and the disk one, this is not applicable to our case, more than 3,000. Okay. Just a remark: these kinds of collectors, they have that's not exactly a problem, but sensitivity. They are sensitive to aeroelastic effects. I'm going back some slides just to explain this here, okay, at our solar tower. What happens is that this kind of mirrors, they start to vibrate because due to wind, for instance, the action of the wind makes them vibrate and deform. So the focal point actually becomes a blur, okay? So you have a loss of efficiency as a concentration efficiency due to the stability, the structural stability of these reflectors here. Okay, so that's something to take into account. Okay, let's move on. Oops, sorry. Let's move on. Now let's analyze this regenerative exchanger here. Okay, so my control volume now is here. And if I look at the primary fluid, we have the same equation as before. Q equals to heat capacity times delta T. Okay. If we look at the secondary fluid, we have a similar equation. Q equals heat capacity times delta T. Delta T now is T3 minus T2. Okay. Of course, if we choose to work with water, I cannot express the enthalpies as Cp times T unless I use the proper Cp depending on the temperature. So if I'm working with water, I should have written something like this: Q equals M H3 minus H2. Okay, so actually we are going to use this formula for the calculations. I'm using this one just to make some considerations about the heat capacity of the primary compared to the heat capacity of the secondary. Okay, so it works well for what I'm going to elaborate right now, okay? Okay, so let me erase this. And suppose it's okay, and it can be okay because we can work with compressed nitrogen, for instance, in this secondary cycle here. So for compressed nitrogen, I can use this formula, no problem, okay? Okay, so since it's the same, we're neglecting all losses, I can replace this equation down here and obtain this formula here, okay? If I look at the temperatures of the hot fluid from Ts, the hot fluid releases heat, so its temperature decreases from Ts to Te. Okay? The blue fluid is the cold fluid. It receives heat, so its temperature increases from T2 to T3. Okay? What happens now if the heat capacity of the secondary is much larger, much greater than the heat capacity of the primary? Okay? So for each energy unit released by the primary fluid, okay, it experiments a temperature drop which is greater than the temperature increase of the secondary for the same absorbed unit of energy. Okay? And as I mentioned, this is not good. Why? Because we want to have very high T3. Okay, we want to increase T3 in order to increase the first law efficiency of the conversion cycle here. Okay, so we have to work in order to avoid this situation, actually. The better situation would be something like this. The heat capacity of the primary cycle, the primary fluid, is much larger than the heat capacity of the secondary. So that's the same analysis for each energy released from the hot one to the cold one. Okay, the temperature drop is smaller than the temperature rise of the secondary. Okay, so this is good because this assures that the temperature at 3 is going to be maximum, and at the limit, if I have a very, very huge area here, T3 is going to become equal to Ts. Okay, and this is, okay, yeah, I wrote this down. If area goes to infinity, T3 tends to Ts. Okay. The problem here is just a practical problem, actually. If T3 becomes too high, I don't have many choices as working fluid. I cannot work, for instance, with some vegetable oil because it's going to degenerate. So I need special oils which stands at very high temperatures. I also need, I can use, and we're going to use in our case here today, liquid salt, but you can also have pressurized water, for instance. Okay, so working fluid here, or the primary cycle, needs to be special in some way, okay, because it has to stand very high temperatures. Okay, so with these working formulas, let's try to define, to calculate some specifications of our power plant, okay. And for this, I'm going to arbitrate some numbers here. Okay. Okay. So our power plant is here. It's architecture, let's say, like its layout. I was looking for this word. And let's suppose some things. Okay. First, suppose that our client already said, oh, I need a power plant that produces 20 megawatts of electricity, okay? And why is that? Because, I don't know, he may be closed a deal in one of those energy bids here in Brazil, and he already signed for supplying 20 megawatts for 15 years, okay? So that's what he wants. he doesn't want more and he doesn't want less. So he already knows the power of his the surplus power of his power plant. Okay. Another parameter that we're going to fix is the efficiency of the conversion cycle, 30%. Okay. And why is that? You know, in some countries, not here in Brazil and especially in Europe, you may have subsidies if you have an efficiency, a certain efficiency above a certain limit. Okay, particularly if you use the rejected heat here, down here at the cooling tower. Okay, so let's suppose that for go on.
I have a basic question, actually. This thermosolar power plant, the sun heat the oil inside the pipe or the water with a salt, but how does the liquid make the turbine spine, you know? This liquid heat the water and the water turn the turbine spine? Is that
Yeah, exactly. I'm going to show you this, okay? But the idea is that the solar energy is absorbed by the primary liquid. Then the primary liquid heats the secondary liquid. And actually, in this case, we have liquid water here. And here we have high pressure steam. High pressure, high temperature steam. So it's going to drive the turbine. Okay? But we're going to see this in a minute. Okay? I'm just explaining this. Okay, I'm just explaining these parameters here, okay, because I want to simplify a little bit the problem, okay. Well, so I justified already why the surplus power is fixed, why the efficiency is fixed, and well, if I know the surplus power and the efficiency, I can calculate the amount of heat absorbed here, okay? Q absorbed, okay, because this is the definition of efficiency. Okay, efficiency is equal to the surplus power divided by the heat absorbed from the hot reservoir, okay? So dividing 20 megawatts by 0.3, I get 57.14 megawatts. So this amount of energy, okay, it's being supplied here by the primary, and it's related to the absorption here at the collectors. Okay. So another point that another parameter that I'm fixing is the temperature. Well, the working fluid also. We're going to work with water. As I mentioned, actually it's a lot better to work with compressed nitrogen here. Okay, with regeneration heat, but I don't want it to complicate and not having additional concepts. Okay, so I'm keeping it very, very simple just to show you. Okay, so we're deciding to work with water here, and also the ambient temperature, the environmental temperature, we're going to say that is 35 degrees. Yeah, sorry for the Portuguese here. Okay. Okay, so and another point is that the area here it's very, very big, very significant, so that the temperature T3 is equal to Ts. Okay, and we are working in this situation here. The heat capacity of the primary is greater than the heat capacity of the secondary. Actually, this temperature drop here, we have interest in having a very small temperature drop here. You're going to see in a few moments, okay? So this is the temperature diagram of the primary fluid and the temperature diagram of the secondary. Since it is a thermodynamic cycle, I'm not only plotting the temperature, but also the entropy to define the state, the thermodynamic state of the working fluid here, okay? We're going to look in details those two diagrams here, okay? In order to start calculating things, Ts, for instance, this pressure here, and so on. Okay. Yeah, so I fixed the temperature here, 35 degrees. So it's the same point here. You see the yellow star here. This is 33 degrees. I'm also fixing environmental pressure here. Okay. But I don't know the pressure, the higher pressure here, the maximum pressure. I'm going to have to calculate this. Okay. So let's start making some calculations. Let's look at the thermodynamic cycle. What do I know about this? I know that the temperature here in point 1 is 35 degrees. Okay, I know the pressure, 1 bar. And I know the amount of heat that is being absorbed because, yeah, as I mentioned, it's 57.14 megawatts. Okay, so what I have to calculate is the temperature Ts, which is equal to T3 actually. Okay, I should have written T3 here. T3. I want to calculate this. So I have a nonlinear problem actually because from this side I know the efficiency 30%, and if I look at the thermodynamic cycle, I know that this is the surplus exergy, which is actually the exergy produced by the turbine minus the exergy absorbed by the pump. Okay, the exergy produced by the turbine is H3, the enthalpy. Okay, H3 minus H4, this drop here, this enthalpic drop here. Okay, and H2 minus H1, H2 minus H1 is the power absorbed by the pump. Okay, so in the numerator here we have the liquid or the net power, okay, the surplus power. The denominator here is the amount of heat absorbed, which is H3 minus H2. Okay, I forgot to write here. In this point we have H3. Okay. Okay, so I have to solve this equation in order to calculate the pressure and the temperature here. Okay, so let's see how this can be done. From this expression here, I can isolate the enthalpy at 3. Okay, so H3 is equal to H2 minus H4 minus H1 divided by 1 minus the efficiency. Okay, I'm using, as I think I already mentioned, I'm using the worst method in the world to solve this equation, which is successive substitutions. It's the worst, but it's the most commonly used. I already showed you more performant methods, but in this case this works well, so I wanted to show you the use of this method. The idea is you start by assessing, okay, the temperature that you want to calculate, and you manipulate, you use all the formulas that you have in your problem in order to calculate the variable that you assessed in the first place, estimated in the first place. Okay, and this goes iteratively. Okay, so let's suppose that we know, TS. It's an estimation of TS. Okay, if I know TS is T3 here. Okay, TS is equal to T3. If I know TS and I know the entropy here, and I know the entropy S3 because it's equal to S4. Okay, so I have two coordinates of this thermodynamic state, so I'm able to calculate P3, the pressure at 3. Okay. Okay, so I use some formula to calculate this, some model of my fluid here. Okay. By knowing P3 and knowing that it's equal to P2 because this absorption here is at constant pressure, okay, so P2 equals P3, okay, and I know that S2 is equal to S1. So I know this point, I know the entropy of this point, so I know the entropy at point 2. So again, I have two coordinates, pressure and entropy, so I'm able to calculate H2. Okay, and now I know H2, I know H1, H4, I know the efficiency, so I can calculate H3. Okay, so, and knowing H3, the entropy at point 3, and also the pressure, which I calculated here, I can calculate T3, okay, which is the temperature that I estimated in the first place. So I can iterate this, okay, and this can be done very easily. I have a spreadsheet here. I can, well, since I have a lot to say today, I'm not going to look at the spreadsheet, but I will publish it on the site so you can download the spreadsheet if you want to take a look at the calculations, okay? So if we perform this iterative calculation here, you see I'm estimating 600 degrees here, and I end up with 641 or 642 degrees, okay? So this is the temperature at this point here, which is the temperature here. So 642 is going to be the temperature here, 642 degrees, okay, which is the same here, 642 degrees, okay? So we have already an important parameter of our calculations, namely the temperature at this maximum energy point. Well, an important point related to this result is that it's very high. Okay, so due to the very high temperature, it's necessary to work with liquid salt. You cannot work, well, vegetable oil, of course not, but mineral oils also have problem working with at this temperature. Okay, so we're going to use liquid salt. Okay. Let's see the possibilities. You have, well, I'm not showing you all the possibilities, I'm showing you the best solution for our case, is this mixture of salts here, okay? And if you look at this equilibrium diagram of this mixture, okay, so here you have temperature, and here you have concentration, and below the red line, everything is solid, okay? Above the liquid line, everything is liquid, and between the two, you have a mixture of liquid and solid. This is an equilibrium diagram as it is this one, okay? Temperature entropy. Except that instead of having liquid and solid, we have gas and liquid, okay? And this region between the transition line, we have a mixture of gas and liquid, okay? And here, between the two lines, we have a mixture of liquid and solid, okay? So the point here is the following. I need to work at 641, which is well above 340 here, but I also have a problem of solidification, okay? I cannot afford, I'm going back some slides, I cannot afford to have temperature here lower than the solidification temperature of the salt. Why is this? Because if salt solidifies here, it's going to block completely the pipeline, okay? And you have to somehow heat all this piping in order to melt the salt in order for it to flow again to the primary. Okay, so one problem of this solution is that our working fluid solidifies. And as I mentioned, if it solidifies, it's going to block the pipeline. So I cannot afford to have a lower temperature at this leg here, okay, below the solidification temperature. So this means that it's better to work with this concentration, 50%, 50%, because that's the lower solidification temperature, okay? So we're going to use this mixture, and our limit lower temperature is 230 degrees. So this number here is we're going to use it to calculate something in a few moments, okay? Okay, so this temperature forced us to choose to work with a mixture of salts, okay? And in this case, we're choosing this mixture and this concentration, which has this limiting temperature, 230, okay? Before moving on, just a calculation of the flow rate of the secondary cycle, because we're going to need to assess the heat capacities of the primary and of the secondary. So I need to calculate the flow rates. Okay, so the flow rate of the secondary cycle is, well, first law of thermodynamics here, okay? So it's simply W, and well, I already solved the cycle, the thermodynamic cycle, so I know all the enthalpies, and by replacing all the proper numbers here, I get 18.46 kilograms per second. That's the flow rate here in the secondary cycle, okay? And as I mentioned, temperature at 2 must be higher than the melting temperature of our working fluid, okay? Okay, so let's try to assess this. What we know, looking now at the primary side, we know that it's absorbing 57.14 megawatts. Its temperature, it's releasing 57.14 megawatts. Its temperature is dropping from 642 to TE, and we know that TE, as I mentioned, must be greater than the melting temperature of the salt, which is 230, okay? We're going to calculate something, the necessary heat capacity. Okay, so this is the primary side, and this is the secondary. Its temperature is rising from roughly 35 degrees to 642, okay? And I'm just recovering an equation that we developed a few slides ago. That's the energy balance of the primary fluid. And we know that TE, from this equation, I know that TE is equal to TS minus the absorbed heat divided by the heat capacity. Okay, and heat capacity, I know this is a charted data. Okay. Okay, so from this temperature, I know that TE must be greater than 230, so now I can vary this, this flow rate here and verify which is the value, the limit value, okay? So this graph here, this equation is plotted here, so I have TE here from this formula, and here the flow rate of the primary fluid, okay, and we get this result. Above 88.93 kilograms per second, we have temperatures higher than 230, okay? I don't know if you observed this, but why am I calculating this number here? Because it needs to be high enough for the temperature to be greater than 230, okay? But I don't want to have a too high, 500 kilograms per second or 1,000 kilograms per second. If I had 1,000 kilograms per second, my temperature drop here would be something like half degree, okay? But this is not interesting because a very, very high flow rate here means that I have to have a very high pumping power. Everything's going to get very big, so it's going to become expensive, both in terms of capex and also in terms of opex, operation and capital costs. So what I want for this flow rate is the minimum flow rate, okay, the smallest flow rate that gives me a temperature above 230 degrees. So that's why I'm making this calculation, okay? So 88.93 is the limit flow rate to have temperatures above 230 degrees, okay? Okay, so two observations. It is necessary to specify an unfreezing system for the salt in case of shutdown, okay? You know, Murphy's Law, when a problem can happen, this means that it will happen. So it means that for some reason, your power plant is going to shut down. You may have, I don't know, 1 week without sun. Very, very cloudy day. It's raining in the desert for 1 week. So you don't have sun, okay? So your temperature, you have no means of keeping temperature above 230 degrees. Okay, so this means that it's going to solidify. So you have to define a unmelting system here. This is actually very simple. You can have electric resistances to heat the piping. You also can have steam, okay, to melt salt here. So this is an important point, but it's not necessary to consider at this point in our class here, okay? Another observation is that it is necessary to specify a thermal storage system, okay, capable of compensating variations of sun's absorbed energy because of clouds, of dust, for instance, okay? So as to maintain a constant heat supply to the secondary during nights or during rainy days, okay? This first point here we're not going to address because it doesn't change the configuration of our solar plant. I mean the conceptual numbers of our power plant, but this point here we're going to address further on. Okay, we're going to do this. We're going to specify this storage system. Just to give you an idea of how we could do this, okay, let's take a look at our power plant, how it's becoming to take shape now. Okay, let's revise everything. We know that the surplus power is 20 megawatts. We need to absorb 57 megawatt from the heat source, okay, from the primary cycle, okay, at these conditions, roughly. Sorry for the Portuguese, 90 kilograms per second at 642 degrees in average, okay? Something that it's important to mention right now is that this temperature, being as high as 642, actually defined the type of fluid that we can use here, but it also defines the type of collector concentrator that we use here. Okay, you cannot achieve temperatures such as 642 degrees with those other types of collectors, trough collectors, and so on. You can achieve this with a disk, but this is typical of a sun tower, as it is shown here. Okay, so our system is going to be like this, a series of mirrors. Actually, these are flat mirrors, okay? They are not parabolic as shown here. So we're going to have a series of flat mirrors reflecting sun's light to this point, to this focal point here, okay? Let's just take a look at the storage system. How can we do? We can use salt as storage system and 2 reservoirs, okay? Just follow my reasoning here. During the day, okay, if I double the number of mirrors here, okay, if I double the number of mirrors, so instead of absorbing 57 megawatts, I'm absorbing 114 megawatts, okay? Half of these megawatts, 57 megawatts, okay, goes to the secondary, and half, okay, flows to this branch here, and it's going to heat salt, liquid salt from the cold reservoir to the hot reservoir. Okay, so during day, we fill this reservoir here, okay, with hot liquid salt. Okay, so we have during the day, at the end of the day, this reservoir is plenty of liquid salt at 642 degrees. Okay, during the night, I change the configuration of these valves here. Okay, so well, we don't have any more salt flowing by the tower, and during the night we reverse the flow here. Okay, so we have hot liquid salt that is heating the liquid salt of the primary here. Okay, so we transfer all this hot salt to this reservoir. It's going to become cold salt, and we are going to be able to supply this amount of heat to the secondary. Okay, so our storage system can be something as simple as this. The only requiring for this is to have additional heating power here, okay, in order to, reflecting to the focal point here, in order to, in addition to heat the secondary cycle, also heat the storage system here, okay, the salt here. Okay, so this is the point. Yeah, and what we need to do now to proceed with our calculations is to determine how much here, okay, I'm making this remark here, how much energy is available for conversion. Okay, why this is not a trivial question? Because, as I mentioned, the amount of energy that arrives here in order to be converted to electricity and to stored energy, the amount varies with the hour of the day, with the day of the year, and depends on the position on the globe. Okay, you know, if you are going to build this power plant on the equator, it's going to have different behavior than if you build this power plant, I don't know, in the South Pole, for instance. Okay, it's not a good idea to build a power plant in the South Pole, but you know, because the angles here is going to be very, very different. So what we need to do to calculate how much energy we have here at, let's say, in a year, in average, okay, I need to assess the amount of solar energy that arrives instantly at a given day, in a given hour, and at our latitude, and at our position on the globe. Okay, so this yellow box here we're going to assess. We're going to use celestial mechanics actually to assess this. Okay, and what we're going to do after assessing solar energy, this term here, we're going to calculate the average energy that is available for conversion. Okay, Q capture in function of latitude. Okay, so we're going to assess it. We're going to make this integrals integrate in 12 hours. Okay, that's why it's divided by 12, because I already know that during the night we don't have sun, and we're going to integrate this over the year, so that's why it's divided by 365. Okay, so I need to do this now, and as I mentioned in the beginning of our class, I need to use celestial mechanics. So now I think I'm going to spend roughly 1 hour talking about celestial mechanics. And an important observation is that everything I'm going to talk about celestial mechanics, it's applicable to this kind of power plant, but also to photovoltaic power plants. Okay, so that's the value of giving you this information. Okay, so as I mentioned, what we need to do, we need to calculate the amount of heat that's coming from the sun. in order to design our power plant, but also in order to move our reflectors during the day, during the hours of the day, and during the days of the year, okay? So we need to track the sun. That's our objective right now, okay? And, well, there's no way to avoid. We need to see how things work. So, you know, Earth moves around the sun. Its orbital path is not circular, okay? It's a ellipse, okay? Elliptical path. You know, it takes a year to complete. It also moves around itself, Earth. It turns around itself, and you know its spinning axis is tilted with regard to this orbital plane here. Okay, so we're going to look in details. Let me give you some definitions right now. Instead of looking from the outer space, let's look at Earth. So this is the rotation axis of Earth, okay? Its rotation takes roughly 25 hours. The cosmos here, we can call this celestial sphere. This is a historical term actually. And the projection of the equator on the celestial sphere, we are going to call this celestial equator, okay? If we project the translation of the sun on the celestial sphere, we have the ecliptic, okay? So the sun moves around Earth. Its axis is tilted, okay? This period takes roughly 365 days, okay? And some important names here, okay? The solstices, summer and winter, or depending on the hemisphere, winter and summer, are the points of maximum inclination here. So in this point here, you have the longest day, if this is the summer solstice, and here you have the longest night, okay, if this is the winter solstice. The point here where the ecliptic crosses the celestial equator are known as equinox. Okay, it's a point where the duration of the day is equal to the duration of the night. Okay, so this axis here, the inclination is 23.5. Okay, and as I mentioned, the ecliptic marks the positions occupied by the sun during the sidereal year. That's the duration. And something I want to stress, because it's also related to climatic changes. I mentioned this in my first class. It's related to the Milankovitch cycles. These cycles, I'm going to show you in a while, are related to the variation of this angle, okay, and several other variations. That we don't need to take this into account for our solar power plant, because the cycles they have periods of 40,000 years, so our power plant's not going to last so much time. But, well, it's related to climatic change, okay? So the equinox is the point here, and we have a meridian here, okay? This white line that joins the North Pole to the South Pole, okay? We're going to start our analysis by a special point. This point here, the meridian crossing with the equator. Okay, so we're going to put our observer there, okay, at this point. So we are on top of the equator on a given meridian. Okay, yeah, just to remind, the term celestial sphere comes from history, because a very long time ago, they didn't know it was space, what was space, and actually they believed that it was a crystal sphere, okay, on top of which you had all stars and objects fixed on. So you possibly could be able to look beyond the celestial sphere. So we use the term celestial sphere. It's not a sphere, okay, it's the universe actually, so it's in infinity. but the term sphere comes from this conception, very old conception. Okay, so our observer is on top of the equator on a given meridian. So what he sees, okay, that's the point of view of the observer. Here is his, he sees north, he sees the south and east and west, okay? And this blue line here is his local horizon, okay? So the observer horizon, okay? The point on top of his head is the zenith, okay? And below is nadir, okay? So I have to give you these names because we're going to use them in our formulas, okay? So this is a part, I'm trying to give you all the needed definitions, okay? When our observer observes the sun at this particular day, the solstice, it sees the sun rising on the horizon here from east, okay? So it goes up 12 o'clock here, and then it sets on the other side of the horizon here. And this is the solstice. So this means that the sun is the farther, that's the maximum inclination here, okay? During the equinox, remember, he's in the equator, okay? During the equinox, the sun rises from the east perfectly, okay? From this axis here. It rises and it sets on west, and this is the equinox. Okay, so I'm going back a few slides here. This means that this day the sun is right here. Okay. Okay, so equinox and the winter solstice, the same thing. So the sun rises on east and sets on west. Okay. So this is what happens when our observer is at this point here. Okay, what happens if he moves, let's say, north to this position here, where I'm pointing at? Okay, let's see. He goes north, okay, and he starts to see the sun in the summer solstice rising. It still rises on the east and sets on west, but the trajectory is tilted. Okay, so and this we know that this is summer because the sun spends more time here releasing energy to our observer during this situation compared with this situation. So the sun spends a smaller time, okay, during winter, okay, and during the equinox we have this situation here, okay. If our observer continues to move north, okay, something interesting happens. Above the Arctic Circle, during summer the sun doesn't set. Okay, so it stays on the sky for the whole day. This is during summer, okay? And during winter, the sun does not rise, okay? So it's below the horizon, the observer's horizon, during all the day, during 24 hours, okay? So that's the origin of the term midnight sun, because at midnight, you still can see the sun because you are above the polar circle, okay, in this case. Okay. Just to start looking at some numbers and some numbers important for our design, our power plant's design, and we're going to calculate these curves in a few moments. The amount of energy arriving on top of the atmosphere during the days of the year and for different latitudes, okay? So you see that in terms of megajoules per square meter per day. So it's an average value, daily value, okay? So you see that near the equator, this varies almost nothing, okay? this variation actually is related to the distance from the sun to Earth, which, you know, vary a little bit. At a latitude similar to ours here in the state of São Paulo, we have roughly half of the energy arriving on winter compared with summer, okay, 40 megajoules per square meter per day compared to 20 megajoules. And at higher latitudes, such as London, UK, okay, you have an even bigger variation, okay? But this is, as I mentioned, what arrives at the top of our atmosphere, okay? Now let's take a look at what happens at the surface, because our solar power plant is not going to build in orbit, it's going to be built on the surface of the Earth, okay? So just for you to see, let's take this blue curve here. This is what arrives at the troposphere, okay? Stratosphere. When it traverses the atmosphere, it loses roughly 25%, 70%. That's an average empirical number, okay? So you have this blue dotted line here, okay? If you consider the presence of clouds and dust in the air and so on, you, in a particular year, you're going to measure, for instance, an actual curve here, okay? This is for a given year. If you measure again the next year, you're going to measure another curve, okay? And if you measure for many, many years, you're going to have a kind of a filled cloud here, showing you the statistical maximum and statistical minimum here. Okay, just to show you how energy is being, let's say, corroded or depleted due to atmospheric absorption and also due to clouds and so on. These curves here we're going to calculate in a few moments. Okay, we're going to have formulas to calculate this. This effect here, the effect of clouds and dust and so on, we're going to assess this through our capacity factor. We're going to set a capacity factor in order to assess this. Okay, well, so this was the example for, in terms of the average daily energy. Okay, so this the result here is the hour energy that arrives, okay, during different hours of the day, during different dates of the year, during different days of the year. So during summer, you see the sun rises before 6 o'clock, okay, before 6 o'clock. This is noon, okay, and it sets after 6 o'clock, 6 p.m., okay. And during winter, the sun is rising after 6 and is setting before 6 p.m., okay. And we're going to be able to calculate all this. Okay, so just a summary of what we need, because now I'm going to show you some formulas, some working formulas, and I'm going to deduce some of them, okay, because it's important to see how things work. Just to summarize what we need, okay, so we have variables that depend on the day of the year, okay, so this is the distance from the sun due to Earth's eccentricity, orbital eccentricity, okay, and we also need to know the position of the sun on the ecliptic, okay, and well, this is a variable. These parameters here depend on the day of the year. We also have parameters that depend on the hour of the day, okay, so this incidence angle, okay, and also the atmospheric absorption. This depends on the hour of the day. And we also have random effects here, clouds, dust, pollution, and so on. And we're going to assess this through our capacity factor. Okay? So, our definitions we have, we already have many definitions, but we need to define our working formulae. Okay? To do this, I'm going to show you these points here. Observers and sun's equatorial coordinates. Actually, I'm going to talk about two systems of coordinates, okay? Equatorial system of coordinates, and also what we call horizontal coordinates, okay? Based on the observer. After defining and knowing how to calculate one from the other, okay? We're going to define the solar versor. Versor, it means, for those of you who are not familiar, is a unitary vector. Okay, so we have to calculate the solar vector, okay, which is the direction or the line joining the sun to the observer. Okay, so with this information we can perform that integral that I showed you in the beginning of this part of the class. Okay. So we're going to calculate in function of the observer position, okay, in terms of latitude and longitude, and of the date, hour of the day and day of the year, okay? And then we're going to calculate the amount of energy that arrives at our power plant. So this is kind of a flight plan for the next, I don't know, 10 or 15 slides, okay? So let's see some definitions. Equatorial coordinates. Equatorial means based on the equator. Okay, so this I think everybody knows. Our observer is in a given position on the globe, so its longitude is lambda. Okay, its or his latitude is phi or phi. Okay, lambda is measured. Phi, let's start with latitude. So phi is measured from the equator to the observer on the corresponding meridian. Okay, and the meridian is the line that starts at the North Pole and goes to the South Pole and passes by the observer. Okay, so latitude is simple. You measure from the equator. Okay, longitude depends on a conventional meridian, which is the Greenwich meridian. Okay, and why Greenwich? Because at the time, okay, the British, let's say, ruled the world, so they defined this. Actually, this is related to navigation. Okay. Related to navigation, and they were the most developed ones in navigation skills, so they defined the Greenwich meridian to measure time, actually. Okay, longitude lambda is related to time. Okay, and yes, I already mentioned. So longitude is measured from the Greenwich meridian to the observer's meridian. Okay, it's lambda. Let's move on. If we project this on the celestial sphere, okay, we can also measure on the celestial equator. You just put the word celestial before everything, okay? So longitude is measured on the equator, or the celestial equator, and likewise latitude from the equator, okay? No problem here. Now, I'm going to give you, because I mentioned, let me go back one slide, okay? The observer's position in terms of equatorial coordinates, so longitude and latitude. What I need now to know where the sun is, okay? Because I need to point my mirrors to the sun. So I have to define the position of the sun in terms of equatorial coordinates. So the sun, let's suppose it's here, in this particular meridian here, at a given position. Just to advance, to anticipate or what I mentioned as being the solar vector is going to be a vector joining the observer, the observer to the sun. So this red vector here is going to be our solar vector. Okay, but right now what I need to do is to define the coordinates of the sun in equatorial coordinates. Okay, so it's the same, only the names are different. So the angle here is what we call hour angle, because, well, it's also measured on the equator, on the celestial equator. And instead of working with hours, 1 hour, 2 hours, we're going to work in terms of degrees, because we're going to work with phi. Okay? So the position of the sun is defined in terms of the hour angle, or simply hour, okay, and also in terms of its declination. Okay, the hour angle, of course, depends on the hour of the day, and the sun's declination depend on the day of the year. Okay, let's move on. Now, I want to change, and I'm not talking about anymore about equatorial coordinates. Okay, now we're changing to horizontal coordinates. Horizontal because it uses the observer's horizon, local horizon, as the fundamental plane, okay, for the construction of these coordinates. So this fundamental plane, what I'm calling here fundamental plane, is the plane tangent to the Earth's surface, passing by the observer here, okay, north, south, east, west. So his horizon, if I am allowed to draw his local horizon, would be something here. Okay, so this is our observer's local horizon, and we're going to build a set of coordinates for the sun to the local system. Okay, so what he sees, okay, is here. Here is his local horizon, the observer's horizon, the celestial sphere, and north, south, east, west, okay, and the position of the sun. In this second situation, we don't need coordinates for the observer because it's at the center, okay, at the center here. The observer is here, okay. So the sun is at a certain point here, okay. This yellow vector here is what I drawn, or a solar verse, or a solar unitary vector, okay. And the coordinates of the sun, we're going to do exactly the same, okay. We're going to measure on the equator, on the horizon, okay, which plays the role of the equator. So we have an angle on the equator, which we're going to call azimuth, okay, and we have an angle on the sun's meridian, the corresponding to the sun's meridian, okay, which we're going to call elevation, okay. So those are simply definitions. The problem is that in a given position on the globe, it's much simpler to work with azimuth and elevation, okay, but all other variables, it's easier to express, to assess in terms of equatorial coordinates, okay, so that's it. Well, this is very simple. This is one definition that I'm going to deduce for you, okay, how to calculate the solar vector in terms of azimuth and elevation, okay. This is interesting. I'm going to do it once, and then the other times this will appear, it's going to be the same, okay. So let's see how it works. You have, well, x, y, and z, and the corresponding I, j, k cursors, okay. And let's see the component on the direction on z, okay. So you see that if you project the solar vector on the z-axis, I'm trying to, sorry. I messed up here. Let me erase. Sorry guys. What I want to show you, for instance, is how to calculate this component here. This is very simple. You simply project this. You project here, okay? So you have 90 degrees here, okay? And to project here, this you simply multiply by the sinus of this angle here, okay? And remember, the modulus is 1, so that's why it's 1 multiplying sinus of h, okay, in this component here. So this is trivial, okay? Now the second part here, okay? If I project the solar vector here, okay, this is 90 degrees. So I multiply this by cosinus of h, so cosinus of h here. So this term here is this term, okay? And if I want to project on the x and y-axis, I multiply by cosinus of azimuth and sinus of azimuth, okay? So it's a simple projection. The formula results apparently complex, but actually is very, very simple. I hope you follow me, okay? So it's very simple to calculate the solar vector, as I showed you, simply by projecting, by using these angles here, okay? Okay. Now we can, I'm going faster now, okay? We can look at the horizontal coordinates. We can look at the sun, or the ecliptic here in the horizontal coordinates, okay? If I pass a plane by the north-south pole and by the zenith, okay? This is the blue plane. And I can define the hour angle here and the declination here, just to see those other variables, those equatorial variables in terms in the horizontal view, okay, horizontal from horizon, okay, just to show you. I can do the same kind of projection. You know, I can use as I mentioned here, okay, elevation and azimuth to calculate solar vector, or I can use the hour angle and declination to calculate, and the deduction is exactly the same, okay? So from a practical point of view, what I need to do is the following, okay? Now we're going to start becoming more practical, okay? I have my observers here, and as I mentioned, I have to point my reflectors to the sun at a given time of the day, at a given day of the year, and for that particular position on the globe. So I need the solar vector. And what I can do for this is, for instance, I get a GPS chip, for instance. You can buy this and plug into your laptop, for instance. And if you look at the string, the GPS string, you get, okay, latitude, longitude, you calculate this, but you also have the time, okay? The GPS signal is also a base of time, a very precise one, actually, okay? So from a practical point of view, with an antenna, for instance, you get a GPS signal, you get all these variables: latitude, longitude, declination, and hour angle, okay? And with these variables, you can calculate elevation and azimuth. I'm going to show you how in a moment. And with elevation and azimuth, you calculate the solar vector, and you use this to correct the position of these reflectors, okay? So you can do this. Just to summarize what we have right now, we have two sets of coordinates: equatorial coordinates and horizontal coordinates. In equatorial coordinates, our observer is described in terms of his longitude and latitude, lambda and phi, okay? And the sun, the position of the sun, it is defined in terms of the hour angle, phi, and the declination delta, okay? In horizontal coordinates, the observer, well, it's 0, 0, it's on the origin of the system, okay? And the sun is defined in terms of its azimuth, A, and elevation, H, okay? So what we must be able to do is to jump from one to the other in order to make all these calculations. Okay, let's start. This one I'm not going to deduce for you because it's trivial actually. The sun's declination. Okay, it varies between minus 23.45 degrees to plus 23.45 degrees. Okay. Yeah, I was looking at the scale. I thought it was wrong, but it's okay. So it's a harmonic variation. I think it's okay. I don't need to deduce this for you. The only observation here, this is an important point. The variable that we're going to use to describe the day of the year is going to be this parameter here, n, which runs from 1 to 365. It's what we call a Julian day, okay? The Julian day in January 1st is n equals 1, then it goes to 365, okay? The problem that we have, you know, that our months, they are irregular now. We took one day from February to pay homage to somebody in Rome, and so that's why August has 31 days. So if you want to convert the actual day of the year, okay, in Julian day, you use this conversion table here. This is not as complicated as it seems, because if you're working in Excel, for instance, you already have functions to do this, okay, built-in functions to do this, and most of these programming languages already have, so there's no problem, okay? So this is how you calculate the declination in terms of n, the position during the day. Let me just go back some slides to show you where you can visualize this. Where here? Yeah. So you, sorry, I get my pen. So n actually is a partition of this, the ecliptic, okay? So that's it. That's the only observation I wanted. So n, I know exactly n equals 1 is roughly here for us. N equals 1. Then it goes to 365 on the other side here. Okay, 365. So that's what the Julian day represents. Okay. Let me go back to my slide. Yeah, where am I? Okay, so the next one, so we already know how to calculate the day of the year. The hour of the day, it's much simple because, as I mentioned, minus 90 degrees means 6 a.m., okay, 6 a.m., and plus 90 degrees means 6 p.m., okay? 6 in the morning and 6 in the afternoon. So when we are going to do our integrations, phi is going to range from minus 90 to plus 90, and that's it. Okay. The sun's elevation, we can solve this formula here to calculate. Okay. So if you want to calculate the sun's elevation in terms of declination and and latitude, okay, you solve this formula. I'm not going to show you to deduce this formula, this equation for you, but it's a simple projection matter. Okay, you look at those spheres that I draw, and you see the corresponding projection. And the same for the azimuth. If you want to calculate azimuth in terms of declination and latitude of the sun. Okay, so you now have all the necessary equations to calculate the solar vector, which we're going to use in a few moments. Okay, let's move on. I'm going very fast because, as I mentioned, I have a lot to say. I hope I managed to finish today. Yeah, these formulas allows us to calculate things like this. For instance, the sun's elevation at noon in a given place, Singapore, which is close to the equator. Okay, so you see that the elevation at noon, okay, so it varies actually very few, from 66 to 90 degrees, okay, during the solstice, and at noon the azimuth is perfectly minus 90 plus 90, or 0, 180 degrees, okay. This, if you draw this on the horizontal coordinates, okay, this means that during summer you are here, during winter you are here, okay, and during the equinox you are here, okay. The same thing for São Carlos, which is 22.01. The sun varies more, okay, you see, you get to 90 degrees here and here, and well, then it goes down here, okay. Yeah, just to show you the results. These results that I'm showing you all correspond to these two formulas, this one and this one here, okay. Yeah, and this is the position of the sun during the solstice and equinox, okay. Okay, so we have all we need to calculate the position of the sun on the sky, as I mentioned, and I'm continue repeating, on a given day of the year, at a given time of the day, at a given hour of the day. Now, what we need to do is to assess the amount of energy at the surface of the Earth that will be available for conversion through our power plant. Okay, so what we need to talk now is to explain how energy is absorbed when it traverses the atmosphere. Okay, so let's see the situation right now. Okay, so we have the sun here on the left, Earth is here, okay, it's tilted X, it's rotating, and at the top of the atmosphere we have this amount of energy arriving, okay. This is also called solar constant. We know this has been measured, okay, 1,367 watts per square meter, okay. This is on top of the atmosphere, okay. And the amount of energy that is going to be absorbed will depend, let me draw something here, on what we call the optical path, okay, the optical path. So the optical path right in this position, sorry, I don't know if you know what happens. I have to put the pen at exactly 9 degrees, or it's going to open the pop-up window, okay. So back, what we call optical path, okay, is going to define the amount of energy that is going to be absorbed. In this point here, the optical path is this one. We're going to name this L0, okay? And if I'm calculating in a point here, the optical path is going to be bigger, okay? So L, a certain latitude phi, okay? So you can already see that you have a minimum optical path which corresponds to the exact observer's nadir. Okay, if the sun is coming through the nadir, to the zenith, that's the minimum optical path. Okay, so that is we have to remember our geometry classes in order to evaluate these things. Okay, so let's start in a particular position. Then we are going to make things more complex. Okay, but we're starting at the the most simple situation. Okay, our observer is at the equator, as you can see here. Okay, he's at the equator and at noon. So his latitude is 0 and the declination of the sun is 0. Okay, so it's noon. Okay. We have an empirical model actually for the amount of energy that you get at the surface of the Earth compared to the energy that you get on top of the atmosphere. ISC is SC is for the solar constant. Okay, is this quantity here. Okay, this is an empirical model actually. Okay, and well, this is an empirical model. So it says it starts from this situation that I'm showing you, and it was measured that the amount that arrives here, down here, is 70% of the amount that arrives here on top of the atmosphere. Okay? When you're not on the equator here, when the optical path is greater, okay, you correct the 70% like this, okay? So AM stands for air mass coefficient, okay, which is defined as the local optical path divided by the minimum optical path. In this case, in this particular case, okay, the actual optical path is equal to the minimum optical path. So L0 divided by L0 is 1. 1 to 0.678 is 1. So you have this empirical formula here. Okay? Okay? And yeah, in L0 has been measured 9 kilometers. Of course, the atmosphere goes much beyond this, but in terms of absorption, 9 kilometers. Okay. Okay. So let's make things a little bit more complex. Okay. Our observer is not anymore on the equator, no longer on the equator. He is in latitude phi here, the position phi. Okay. As I mentioned, at noon. Okay. So what I have to do now is to calculate the corresponding optical path, this path here, from this point to this point here. Okay, we're going to do it in a moment. We have to draw some triangles and use some of those geometry classes that we learned a few decades ago. Okay, so the empirical formula is the same. What we have to do is calculate the actual optical path. Okay, and this is simple actually. If you recognize that this angle here is the same as this one, things become very simple. Okay, so if you recognize this, okay, omega equals phi, then you can use this triangular relation here, which I'm going to deduce in the next slide actually. Okay, so you are able to calculate the air mass coefficient in this situation. Okay, so the triangles that I was talking about are those. Okay, so you see our observer here. Okay, and the sun is coming in this direction here, through this direction here. And we need to calculate this this segment here. We need to calculate this length here. Okay. Yeah. Okay. So let me see next slide. So we define some triangles. Actually, I don't know if I'm able to use my marker. No, it's not going to work. So I'm going to get my pen. And let's see, just to show you the triangle that I'm using this triangle here, okay? This is a rectangular triangle, and it is divided by this line here, which is the actual optical path that I want to calculate. So you know from the geometry classes you have two right triangles, okay, and you can use this formula here. Okay, oh sorry, I'm a little bit of perfectionist, so you can use this formula here for L omega, and if you divide by L0, you get the corresponding formula that was in the previous slide for the air mass coefficient. Okay, so it's very simple. And this model here is what we call a spherical model. Okay, you have other models to assess the air mass coefficient. I'm going to show you one and then make a comparison. Okay, this model here that I just deduced for you assumes that absorption is independent on the altitude. Okay, so it assumes that the atmosphere is homogeneous. Okay, we know it's not. We know the density here in these lower layers here is greater than the densities in the upper layers. Okay, so the density of the atmosphere varies, the temperature also varies. Okay, so the absorption is not the same depending on the altitude. So you can take this into account. Some researchers did this, okay, and they got this model for the air mass coefficient. It takes into account also diffuse radiation and the variation of the density of the atmosphere here, okay, and here the variation is much less, okay. You can take this into account through this type of models. And there are several others. I want to show you some, okay. The one that I showed you is the what we call spherical model. But the point is that they start to become significantly different at very high latitudes, okay? 82 degrees, for instance. Below this, all models are the same. So there's no point in using a complicated model if we are not going to work in this region here, okay? So I'm showing you just to justify the fact that we're going to use that kind of a naive model that assumes that absorption is the same no matter what altitude, okay? This is because we're not thinking in building power plants near the poles, okay? So that is why we're going to use the simple model, okay? Now, the last thing we need to do is we need to assess the most generic situation, okay? Declination different than 0 and latitude different than 0, okay? So it's actually simple. If you know that delta is less than 0, okay, is different than 0, okay, you simply calculate things in terms of a relative angle, as I'm showing you in this picture, okay. So you proceed exactly like this, is as simple as that. Instead of omega, you write phi minus delta, just to account for the declination being different than 0, okay. So what you get for your air mass coefficient with the spherical model is here. Okay, so it's very, very simple to assess the more generic situation here. Okay? Okay, so we now have everything. We know how to calculate the amount of energy that arrives in a certain position, a certain latitude, in a given hour of the day and during the days of the year. Okay, we know how to do this. The amount of energy, I omega here, okay, we know how to calculate this in function of everything, and we also know where the sun is going to be, because we know the sun vector. Okay, so what we need to do is to use these formulas in our solar power plant design. Okay, before going there, let me just show you some things. I forgot to do something. Let me just stop my presentation because I wanted to show you something. I have a simulator for the solar system, and I can show you the actual position of the planets, okay, in this simulator. I forgot to open the software here, so I'm just And I wanted to show you before going back to our, let me stop. Okay. Oh, sorry. Where was I? Yeah, here. Okay. Sorry for this. I forgot to open the software. Okay, so we have everything we need. Just a few remarks before. We have the sun vector. We have an equation to calculate sun's elevation. We can see this on the celestial sphere. Okay. This, as I mentioned, the sun is going to rise here. Let me get my pen. Okay. So here, phi equals minus 90. This is 6 a.m. or around 6 a.m. Okay. At noon, phi equals 0. Okay. And here, phi equals plus 90 degrees. So this is the sun, and our solar vector points to the sun. Okay. If we define this plane between the zenith and the solar vector, okay, we can plot the azimuth and the elevation of the sun, as I mentioned, okay, and also the hour angle, the equivalent of an hour angle omega, which is, in this case, it's easy to see, it's 90 minus h, okay. So this summarizes everything, our working formulas. Here, how to calculate the sun, solar energy that we get on surface, the air mass coefficient, and how to assess sun's elevation, okay, and other geometrical formulas here. And these formulas can be used to calculate these graphs that I have already showed you, okay. The solar irradiation at noon during different days of the year. You see how much this varies along the year for a place in Germany, for instance. And even though the solar energy is very small during winter, they have, I don't know, 100 times the amount of solar power plants, photovoltaic or thermal, in Germany. 100 times more than we have here in Brazil, even though they have much less energy during winters, okay? Yeah, I have these numbers here. It's one order of magnitude different, okay? Yeah, before going back to our solar power plant, I want to show you the relations of these celestial mechanical aspects to climate, to our climate. Okay. I'm sure I already mentioned this in the first class, but now I'm able to justify. Okay. First, I start by saying that the Earth is not moving around the sun. Okay. Actually, the Earth is moving around the center of mass of the solar system. Okay. So this means that it's going to be influenced by the sun, of course, but also by the other planets. And these influences will create changes in Earth's orbital movements, okay, in the plural, okay? Let's see some of these movements. First, related to orbital eccentricity, okay? Earth's orbit varies from a flatted ellipse here, okay, and in periods of 400,000 years, it goes from a very flat ellipse to a more circular ellipse like this, okay? And this has a period of 413,000 years, okay, roughly. It also has obliquity, okay, so the inclination of Earth's rotation axis with respect to the sun here, okay, its inclination varies along the years, okay. The period here is 41,000 years, and it varies between 22.1 and 24.5, okay. Also, the most famous one is Earth's precession, okay, which is like a top here, okay. That's the movement, and the period is 26,000 years, okay, for a single period. Okay. I mentioned that this has to do with the amount of energy that arrives on the top of our atmosphere, because, for instance, if you are here, if you have this more eccentric orbital movement, you get far less solar energy than here in this situation here. Okay, so our solar constant, it's not actually that constant. It's going to vary in periods of 400,000 years, but it's sufficient to to provoke climate changes. Okay, if you plot, let me show you the simulator to explain why we have these kinds of movements, influences. Okay, and as I mentioned, they are related to the influences of other planets. I'm going to the simulator. I'm going to show you. Okay, let me take some zoom. Okay, so you see, for instance, in a particular situation, I may speed things, like for instance here in this situation here. Okay, you see of course, the mass of the sun is predominant. Okay, things are not in scale here. Okay, and in this situation here, Earth is actually being accelerated. Why? Because Jupiter is attracting Earth here, okay, and also Saturn in this situation. So in this period of the year, Earth is being accelerated, okay, because you have these two planets pulling Earth towards them, okay. A few months later, okay, Earth is being decelerated, okay. Why? Because of the same reasons, okay. And if you let time pass, you know, depending on the configuration of the planets, you're going to have different influences, okay. And also they have different, not only the positions of the planets, but also the inclinations of their rotation axis, for instance, okay. So all these influences that I showed you on the presentation, eccentricity, precession, and so on, they are created by these kind of influences over here, okay. Another funny thing actually to say is what we call here in Brazil the mapa astral, okay. This kind of map, actually, I'm gonna use my birth date, okay. So I was born on 1962, okay, November 13, 1962, at 22:30. So I was born exactly this time. So what we call mapa astral here in Portuguese is giving value, assigning values to a certain kind of configuration here. So this alignment here, Earth, Venus, Mercury, and the Sun, you have an alignment here, okay? And you can say, well, he's going to have a lot of hair, for instance. So you see, it's not very good. But, well, that's it. If you can, in this simulator, you can speed things up, for instance, and you see that you have all kinds of alignments here, okay? You're always going to have alignments, and if you conclude something from these alignments, yeah, that's your job, okay? Okay, let me stop here and let me go back to our presentation. So, as I mentioned, these other non-trivial orbital movements are related to the influences of the planets of our solar system, okay? And also to Earth's movement, okay? It's a very complex dynamic system. But if you, it's deterministic, okay? If you calculate, I'm going back some slides, if you calculate the influence of these movements, for instance, in this quantity here, what we call solar constant, because this is easy, you just integrate the amount of energy that is arriving on top of the atmosphere, okay? If you account for this very slow variations for 100,000 years, 40,000 years, and 20-something thousand years, if you account for this and you plot this on a graph, you get this blue curve here, okay? So this is the amount of energy, the variation of the solar constant due to what we call Milankovitch cycles, okay? I forgot to mention, these movements generate what we call Milankovitch cycles, okay? So that's it. If you take the Milankovitch cycles into account and calculated the solar constant, you get this blue line here. And this blue line, the x here is in million years, okay? So 600,000 years ago, okay, we see that the total sunlight is varying a lot, okay? The black line here is the actual temperature, average temperature on Earth, okay? So you see that the correlation is very strong between the actual temperature and the amount of energy, the amount of solar energy that we get here on Earth, okay? So this explains most of the temperature variations, okay? This means that the sun really influences climate, okay? Another important observation is that we know already what's going to happen in the future, okay? We know that temperature in the future is going to drop, okay? But I'm not talking about 1,000 years, okay? I'm talking about 100,000 years. Okay, so in 100,000 years, the temperature is going to drop drastically, actually. Okay, we're going to enter a new glaciation period. Okay, and that's it. That's due to solar energy, simply. Okay, we know that in the next 100 years and possibly in the next 1,000 years, temperature is going to rise. Okay, because it's been rising for almost 8,000 years. We know, but due to this Milankovitch cycles in 100,000 years, it's going to drop, okay? And there's an additional effect is the influence of our greenhouse gas emissions, okay? But this happens in a very short period of time compared to climate typical periods, okay? Another important point in this graph is, although we see a strong correlation between the total solar energy and the average temperature, actual temperature, okay, for some periods you don't have a good correlation. For instance here, and for instance here, okay, you see temperature should be rising and it's dropping drastically here in this period. The same here. And this is because it's not only the sun that influences our climate. You also have more, let's say, terrestrial reasons. For instance, the relative position of continents also influences climates. You know, the continents move on the surface of the Earth, and depending on their relative positions, you have different ocean currents. Ocean currents distribute thermal energy throughout the globe. So depending on these positions, you have a more intense distribution of this heat that comes from the sun, or not. Okay, so depending on the position of these continents, relative position of the continents, you also have strong influences on the climate. And there are several other aspects. For instance, the amount of CO2, the amount of greenhouse effect that we have also influences this average temperature. Okay, so you have several factors influencing temperature on Earth, average temperature on Earth. Okay, but the influence of the sun, of these Milankovitch cycles, of course, they are very significant. They cannot be neglected. Okay, but you have to take into account actually the proper period of time. You are talking about at least tens of thousands of years. Okay, and 100,000 of years is a typical period here. Okay. Okay. Let me see time. Okay, I think I'm going to be able to finish the class. So let's come back to our power plant's design. We did this in order to assess the amount of energy that we have available for conversion. Let's just remember things here. Okay, we already have a part of the configuration of our power plant here. Okay, I was telling you that we need to assess how much energy we're going to have at the place where we're going to build our power plant. Okay, we know the amount on top of the atmosphere is 1,367 watts per square meter. Okay, and we know that this is going to be absorbed during its transit through the atmosphere. Okay, so what we're going to do is to integrate this during the whole year. We're going to do this calculation here. Okay, so 0.7 to the air mass coefficient and so on. This is the amount of energy that arrives on the surface here, depending on the sun's elevation, h, okay, in function of the hour of the day and in function of the day of the year. Since we want to calculate an average number, which will depend only on latitude, okay, on the place that we're going to build our power plant, and we need an average number because we simply need to calculate the amount of mirrors that I have to have. Okay, we are integrating this during the day and during the hours of the day and during the days of the year. So this is why I'm dividing by 180 degrees here. Okay, because it goes from minus 90 to plus 90. And I'm also dividing by 365 because we have 365 days in a year. Okay, I'm also multiplying by 12, divided by 24, because I have 12 hours of sun, roughly of average sun, in 24 hours of day. Okay, so this formula here is to calculate the amount of energy that we have to convert to electricity in the average amount in a year. Okay. Okay, so we can plot this in terms of the latitude of the place. So this is, I'm not showing the formula, but it's on the previous slide, is this formula. I'm simply varying phi here. Okay, so you see that on the equator you have 300 and something watts per square meter. This is an average number. Actually, if you go to a supplier to buy a sun heater for your home, he's going to make calculations with this number, 300 watts per square meter, okay, or something close to this. Okay, on the equator, a little bigger. In São Carlos, around, I would say, 325, but you have to multiply it by the capacity factor. Okay. I've mentioned that we are going to build in Chapada do Araripe, in Piauí. The latitude there is -7, so we get 7 degrees. It's almost 325, 340 something here. Okay, so in Piauí, we can plot during the days of the year. This is the amount during the days of the year, okay? And if we calculate the average number, which is the same here actually, 336.4 watts per square meter. This is the average amount of energy in Chapada do Araripe, Piauí, okay, during the year. But disregarding effects of clouds and dust and so on, okay? Is there any doubt on this calculation here? Okay. So what we need to do now is to decide what type of mirror we're going to use. We can do this by the same formula actually. Okay, if I use a fixed mirror, as in this case here, okay, so I have to project, okay, the amount of energy that arrives on this vertical line here. So this means multiplying by sinus of the sun's elevation. Okay, so that's why in the formula appears sinus of h. Okay, because the amount of energy must be projected to this vertical line here. So when we do the calculations, okay, for 7 degrees and for 45 degrees, we get these curves in terms of average watts per square meter during the hours of the day. And this is for a heliostat, okay? We don't have to project because it corrects the position. It corrects for h, okay? So we don't have to multiply by sinus of h here. And we get this red curve here for Piauí and this one for 45, just for comparison. Okay, actually the average number here, okay, we get with this kind of mirrors, they are more expensive, of course, they are more expensive, but you have 36% more energy in Piauí. Okay, so this is, well, it's a significant increase, but in a higher latitude, you have astonishing, I would say, a very significant increase. So, if you were to build this power plant in high latitudes, I would say it's impossible not to choose this kind of mirror. Okay. Okay. So anyway, we're going to choose this one because it's going to become smaller. The number of mirrors is going to be smaller. Okay, so the number that we're going to use to calculate the total reflection area is this one, 672 watts per square meter. This is the daily average. Okay, so let's see what we get. Okay, this summarizes a lot all our results. This is our power plant. Okay, we already have results for this configuration, but let's see what's happening with solar energy. We have this amount arriving on the atmosphere. We lose 70% roughly, okay? So we get 672 watts per square meter on the surface. And if we consider clouds, dust, and so on, this means that we are enforcing a capacity factor of 60%. We have 470 watts per square meter with that kind of heliostat in Piauí. Okay. We also have to consider that I only have this amount of energy 12 hours in 24 hours. Okay. So what we have to do now is the following. This black line here is the amount of energy during the day, okay, so minus 180, this is 0, okay, midnight, okay, 12 o'clock, and then midnight again. This is 24 hours, okay? Okay, so this black line is the amount of energy supplied to the secondary cycle here. So it's 57 megawatts. It's here, okay? And this black line is equal to the sum of what I get from the sun and what I get from the storage system, thermal storage system. Okay, so from the sun, I already calculated. Okay, is this red line here. Okay, so I want a constant supply of heat to the secondary cycle. This I calculate from all those celestial mechanics formulas, and then the amount of heat that goes to the storage system is the difference, the blue line, the black line minus the red line, okay, is the blue line. Okay, so this means that during the day I have to generate energy for both the secondary cycle and for the storage system. Okay, that's what this number means. So in terms of a Sankey diagram, this means that during 12 hours during the day, I have to absorb twice this number, 2 times 57 megawatts, which is 114 megawatts, because during the night this absorption is going to be 0. Okay, half of these 114 megawatts goes to the secondary cycle, 57 megawatts, and this during 24 hours a day. Okay, and the other half goes to the storage system. During 12 hours a day it's negative, and during the other 12 hours of the day it's positive. Okay, so that's what's happening on the Sankey, in terms of a Sankey diagram. Well, we have our number actually, 114 megawatts. Okay, so this is actually equal to the average solar energy, which we just calculated here, okay, times the absorption area. Okay, this must be equal to 114 megawatts. Well, when we make the calculations, 114 divided by 470, okay, we get an area of 25 hectares. Okay, 25 hectares. Roughly an area of 500 meters, a square of 500 meters per 500 meters. Okay, and this actually corresponds almost exactly to one of these units. This is a coincidence actually. Okay, since they have the same nominal power, I started by setting the same nominal power, 20 megawatts. I ended up with almost the same area. Okay, so in this is an actual power plant in Spain. Okay, and this is its configuration. So you have 1,255 heliostats of 120 square meters. Okay, and this shows that all these calculations that we did were very simple. We disregarded many aspects, but even though we get a close result to an actual power plant. Okay, and well, if you ever need to do this in the future, you simply have to follow these guidelines and eventually add some complexities that we're not considering in this class here. Okay, I think this is it. Yeah. Does anybody have a doubt on the subject? Okay, I'm happy I managed to finish the class. Just an observation, some guys are asking, some people is asking about how to get notifications when the channel is transmitting live. What you have to do, when you sign a channel, when you subscribe a particular channel on YouTube, you just have to click on this little bell here. Okay, let me zoom. You click on this little bell here and you are able to configure the warnings, the types of warnings and the frequency of warnings that you get from a particular channel. So for those of you who want to get notifications from my channel through which I'm transmitting this class, not only this class, but the other classes I'm lecturing this year, this semester, you may configure in this place on the channel. Okay? Okay, so yeah, we managed to finish on time. Thank you very much. See you after next week. Thank you.
Okay, teacher, thank you. Teacher, you said you'll see us after next week?
Sorry? Because next week we have a holiday. Is that correct?
Oh.
Let me.
Okay. Yes. November 2nd.
Yeah, it is.
Okay. Thank you.
It's the same for you, okay?
Yeah. John, are you okay? Yeah.